Before computing an example, let me mention a couple of recent papers that use Pukhlikov-Khovansky ring. This is the original paper from 1992. And there is a recent preprint by Askold Khovansky, Ivan Limonenko, and Leonid Monin. Leonid Monin is present at this conference. So if you are interested in the most recent developments on Pukhlikov-Khovansky rings, please ask Lenya. There is also a paper by Khovanskii-Pukhlikov and Elise Villela. And in my talk, I will mostly focus on paper by Naoki Fujita. I will retell his results from a more geometric perspective. Naoki uses representation theoretic considerations. So let me now give an example of an actual computation of Pukhlikov-Khovansky ring. Again, we consider the trapezoid. The family of virtual polytopes analogous to this trapezoid depends on 4 parameters. So we have 4 derivations. And it remains to compute the volume polynomial, which can be easily done by a formula from high school geometry. And it is clear that the volume does not depend on x0, y0, because the volume does not change under parallel translations. So this means that Pukhlikov-Khovansky ring is actually the ring of polynomials in 2 variables, dA and dB, quotiented by the annihilator of the volume polynomial. Of course, we can explicitly compute differential operators that annihilate the polynomial ab plus a squared over 2. We might also get some insight if we remember that the trapezoid is a Newton polytope of the blow-up of P2 at one point, and hence Pukhlikov-Khovansky ring is isomorphic to the Chow ring of the blow-up of P2. However, there is a more convex geometric way to compute relations in Pukhlikov-Khovansky ring, and to do this, we have to choose more natural coordinates, namely every facet of a simple polytope defines a coordinate on the space of all virtual polytopes. For instance, we can fix the origin and measure the distance from the origin to each facet. In this example, we will get 4 coordinates. So let me label facets, in this case, these are edges, counterclockwise. Then coordinates will be labeled by the same indices as faces. We have 4 coordinates, x1, x2, x3, x4, corresponding to the distances from the origin to the facets. And we may alternatively write Pukhlikov-Khovansky ring as the ring of polynomials in d1, d2, d3, d4, quotiented by the ideal. And here we have to rewrite the volume polynomial in new coordinates. So we have these coordinates x1, x2, x3, x4. And it is clear that A is equal to x1 plus x3. With B, it's slightly more complicated, but still an easy geometric problem. And we get a scary expression. At the first glance, it seems that the problem became more complicated than it was in coordinates A and B. However, there is a purely geometric way to describe this ideal based on incidence relation between faces. For instance, we may notice that d1, d3 is 0 modular ideal because d1, d3 annihilate the volume polynomial. And this is the direct consequence of the fact that the corresponding faces, E1 and E3, do not intersect. So the intersection is empty. Then we have 2 linear relations in the ideal, d2 minus d4 and d3 minus d1 minus d2. They come from the fact that the volume does not change under parallel translations. And we have basically 2 parallel translations by vertical vector and by horizontal vector. And all other translations are linear combinations of these. So if we translate by vertical vector, it is clear that we gain something that corresponds to face E2, and we lose something corresponding to face E4. And these two pieces are equal, so that means that derivative with respect to x4 is the same as the derivative with respect to x2. And similar consideration with horizontal parallel translation yields the relation between d3 and the sum d1 and d2. So computing in the Khovanskii-Pukhlikov ring is easy because we can use geometry instead of algebra. Because of this geometric essence, the polytope ring is very useful for positivity questions. And these are questions that usually arise in Schubert calculus. So the main message about polytope rings is that derivations can be associated with linear combinations of faces. Well, if we speak about derivations of order 1, then we'll get linear combinations of faces codimension 1. And product in the polytope ring corresponds to the intersection of faces. Again, as in the case of Chow rings, we should make some assumptions of transversality. And the main question that I'm going to answer in my talk is how to interpret push-pull operator in convex geometric terms. So let me recall what push-pull operator is. Suppose we have a smooth variety X and a vector bundle of rank 2 on X. I will only focus on this example, though of course push-pull operators can be defined for vector bundles of arbitrary rank. So let us consider the variety of all lines in E. Then there is a natural projection from Y to X, which I denote by P. And then there are push-forward and pullback maps in Chow rings of Y and X. And while pullback is a ring homomorphism, push-forward is a more complicated operation, so it's not a ring homomorphism, just homomorphism of abelian groups. And if we take the composition of these two operators, we will get certain operator from Chow ring of Y to itself. So my goal is to give a convex geometric interpretation of this operator. So I will now go to purely convex geometric definition. Of course, since we are talking about projectivization of a rank 2 bundle, the corresponding polytope, for instance, Newton-Okounkov convex polytope, or maybe polytope obtained from some other consideration, this polytope will be quite special. And so I will consider the case when I have a polytope P that corresponds to some hypothetical variety X, and another polynomial Q in the same space, and then delta, which can be thought of as a polytope of Y, will be the Cayley sum. So let me recall the definition of the Cayley sum. So we put, we add extra dimension to RD, and we put P on the first, on the 0 level, and Q on the first level, and take the convex hull. So the example here comes from the following algebraic geometric situation. So let X be P2, and on P2 there is a natural rank 2 vector bundle, namely we can take the tangent bundle. And if we take the projectivization of the tangent bundle, we will get a non-toric variety, because tangent bundle is not split. And actually this non-toric variety is isomorphic to a Fleck variety. Again, as we know from toric geometry, the Newton polytope of P2 is just triangle. And to get the Newton-Akunkov polytope of Y, we take polygon Q, which is just the trapezoid. So it's not hard to check that there is a certain Newton-Akunkov convex polytope corresponding to this variety Y, such that it is indeed the Cayley sum of P and Q. Here I put Q on the 0 level and P on the upper level because I like this picture better, but obviously if we interchange P and Q in the definition of the Cayley sum, we will get the same polytope up to a reflection. And here you see that there is a vertex which is not simple, and this reflects the fact that the variety Y is not toric. It is smooth variety, but not toric. So my goal is to define mitosis operation. In convex geometric terms, that means that for any face F of the polytope P, and I assume that P is embedded in delta as a facet, I will define a collection of faces E1, so on, Ek, whose dimension is greater by 1 than the dimension of F. And I also assume that all these faces contain a fixed vertex of P. So I fix the vertex V, and mitosis operation will depend on V. And morally, this mitosis operation corresponds to push-pull operator in the cases when our polytopes correspond to certain algebraic varieties. So for instance, in this example with P2 and the tangent bundle on P2, it is easy to show that if we identify the Chow ring with the Pukhlikov-Khovanskii ring of the polytope delta, it's not hard to show that they are isomorphic, then push-pull operator of the face F, so this is the edge on top of delta. So this face will go to the sum of two-dimensional faces, E1 and E2. So now I'm going to give a purely convex geometric definition, and this is my main definition. So we fixed a vertex V. And again, I will illustrate this definition by the same picture, only now I will assume that the polytope P is on the 0 level and polytope Q is on the top level. So I will define the set mitosis V of F by 3 conditions. So the face EI belongs to this set if and only if the following 3 conditions are satisfied. And again, all faces that will appear in this definition should contain the vertex V, which I fixed from the very beginning. The only exception is the face Q, which obviously couldn't contain a vertex from P. So the first condition is that EI is not a horizontal face. So we have 2 horizontal faces, P and Q, and EI shouldn't lie in any of them. So EI should be a non-horizontal face. The second condition tells us that the intersection of EI with Q is somehow degenerate, so it is contained in the intersection of the expansion of F with Q, where expansion is a unique phase of delta such that its intersection with P is exactly F. And here I would like, for simplicity, I would like to require that the vertex V is simple. If the vertex V is simple, then it is clear that there is a unique phase exp, expansion of F or exponent of F, such that its intersection with P is exactly F. And I assume, of course, that expansion of f is, again, not contained in P, so it's not a horizontal face. So for instance, in this example, exp of f is this two-dimensional face, and its intersection with P is exactly f. And it is important to note that exp of f is always contained in the set mitosis V of f. So there is always at least one offspring, assuming that f is contained in P. And the third condition is the longest, and also it is the most useful in actual application of mitosis, because it rules out facets of delta that cannot contain EI. So suppose we have a facet gamma, which does contain EI, and again, it should also contain V. Then either this facet also contains F, but if it doesn't contain F, then it should satisfy the following condition. There exists a face H, again, it should contain the vertex V, such that the intersection of H with Q is not in general position with gamma. What does this mean? This means that the intersection of H with delta, if we intersect it with gamma, will have dimension smaller than expected. So in usual transversality condition, the dimension of intersection should drop by 1, because gamma is a facet, so the dimension of intersection should drop by 1. But if it drops more than by 1, then we have something like tangency. So this is the geometric meaning of this condition. And of course, we assume that the intersection of H, Q, and gamma is not empty. So it has smaller dimension than expected, and it is not empty. And this is quite a useful condition. In examples from Schubert calculus, this condition actually allows to compute mitosis explicitly in purely combinatorial terms. So this is the main definition. It looks mysterious, and I am now going to explain how it fits into Schubert calculus. And the main tool will be Gelfand-Setlin polytopes in types A and C.